2. Okay, so here's this function f. And we want to find out what these integrals are. And remember what is, so now in the area, or the geometry perspective, these integrals mean not net change, but like net area, right? Net area. So anytime that the function is below the x-axis, the area carved out will be a negative contribution to the integral. Anytime the function is above the x-axis, the area above the x-axis will be a positive contribution to the integral. Okay, so for this first one from 0 to 2, what will that be? So let's call this let's call that A1, that whole thing there too, and then A2 here. So in terms of A1 and or A2, how could we express what the first integral is, 0 to 2, 5 fx? So first of all, the 5 is just 5 times that integral. So 5 times what related to A1 or A2 would give us this answer? No, related to in terms of A1 and A2. So if we're going to write what this is in terms of A1 and A2, it'd be 5 times what? For instance, A1 plus A2. It would be one possible answer. Just A1. There'll be 5 A1. Is that right? Negative, right? So the function's always negative there. So the integral from 0 to 2 is going to give you the opposite of area 1, right? It's going to be a negative value. So now we just, knowing that these are semicircles, we can just use the geometry formula to find that. What is A1? So that's going to be pi r squared. So negative pi, the radius is 1, but it's only half a circle, so maybe it's like this. So because the function has negative values there, the integral is going to, the net area will be negative, and they'll be in what amount? Half of the area of that circle. So negative pi times 1 squared all over 2. Doesn't make sense. Any questions on that? So 5 times negative pi, 1 squared is 1, divide by 2. Just simplify it that way. Okay, 0 to 6. 0 to 6, which would be this whole, all the way from here to here. How could we express that in terms of A1 and A2? So again, we'll just pull the 5 out, that's fine. 0 to 6. I want to write that as 5 times what in terms of A1 and A2? Okay, he's offering up A2 minus A1. That's right? Because for A2, you're going to get all this positive contribution, and then this area here will be the opposite of this area. So it'll be A2 minus A1. So A2 is the same thing, but now our radius here is 2. So it's going to be positive pi times 2 squared, half of it, minus this one what we had before, pi times 1 squared over 2. Okay, stop me if I lose you. Is this making sense? So that will be 5 times pi, 2 pi, so that would be 4 over 2, minus pi over 2. And with web work, you can put in expressions. It can be your calculator for you. So then you eliminate the possibility of making a punching error on your handheld or a decimal rounding error. You can put in long, complicated expressions. You can also use the preview answer to not waste an attempt, and that gives you a really nice image. So you make sure you're putting in what you intend to put in. So, yeah, so use graphing calculator or web work as the calculator, right? Put expressions in, and then check them with preview answer to make sure, sometimes when you have a horizontal expression with lots of parentheses, it's very tough to see if you got your parentheses right and if it's really setting up the expression you want, or with a preview answer, you can see it. So take advantage of that. Okay, next one, from 1 to 4. From 1, 2, 3, 4. Okay, well, this is basically the same as part B, but now we have quarter circles, right? So it's going to be this quarter circle area minus this quarter circle area when you go from 1 to 4. So we'll leave that one alone. That's basically, it's just going to be half of this, and it'll be just like part B, but then half of each of those, because you're doing a positive quarter circle, positive quarter circle. Last one, the absolute value. The absolute value. So what's that going to be about? So if you take the absolute value of this function, what will happen to this first part? Yeah, it'll turn it positive, right? All those y values will become positive, and then what will happen to the second part? Stay the same, right? It's all positive already, so stay the same. So that last one would be like doing this integral of that blue function. And what, in terms of a1 and a2, will that calculate? So now I've got to make an expression that I can actually do here. So it's going to be, I can pull out the 5, no problem. From here, this is 1 to 6, though. So it's going to be from... So we're going to start here from 1 to 6. What expression in terms of a1 and a2 will get this integral correct? He wants a1 over 2 plus a2. Right, because now the whole thing's positive. So we want a quarter circle of a1, just from 1, because it goes from 1 to 2. It'll be a quarter circle of that smaller radius, and then the full half circle for a2. So it'll be a1 over 2 plus a2. Put that one in. So it'll be 5 times, a1 will be pi times, now it'll be 4 over 4, right? So it'll be a quarter of the circle, so just pi. And then plus, what? A2, which is half of the big circle, pi times 4 divided by 2. Okay, so those, let's see about those 3. Uh-oh, what did I draw? So, oh, I didn't take half of that, a1. So I need, let's see, so pi times, oh, right, so half of that. Thank you. There we go. Okay, questions on this example? Does it make sense? Next one. Okay, so here we have this. The region, my particular problem is 4x minus 1 from -2 to 6. So I'm going to sketch this. So always make sketches. These are geometry problems. You need sketches, okay? You need sketches. Okay, so -1 is the y-intercept, and we're going to have a slope of 4. So it's going to look something like this. And we're going to go from -2 to 6. And what does it want? Notice what it asks for. It says find the area of the region. What does just a straight up integral find? Net area, right? Net area. If you just take this and just go -2 to 6, 4x minus 1 dx, what's that going to find? Is that going to find area? It's going to find a difference of areas, right? It's going to find a difference of areas. You're you're going to get this triangle as a positive contribution, and then this triangle over here is going to have a negative contribution to that. Okay? It wants area, so what do we need to do? So we can put absolute value, but then in terms of solving it, we still have to get rid of those absolute values. We have to figure out where it's positive and where it's negative. So, yeah, we're going to have to find this point, y equals 0, and that's going to be at, is that 1/4? And then how are we going to now calculate, so no, it's not equal to that. So we know that this equals net area. So to get area, we need to add them together. So we need to add those. So how are we going to use an integral to get this area here? It's going to be the opposite of, so we know that's going to give us a negative value, the opposite of that area. So if we take the opposite of it again, it'll be positive. So from -2 to 1/4 of 4x minus 1. And then we can just add this integral because we know that's going to be an area. Plus 1/4 to 6, 4x minus 1. So we could do antiderivative and plug in, but that's actually the kind of the longer way to go here, right? Because of the nature of this function as being a line, there's a much easier way to do it. So in terms of computation, right? So this is perfectly valid. We take the opposite of the integral wherever it's below, and then take the positive version where it's below, and that's going to truly get us area. Whereas just the integral from -2 to 6 is going to subtract those two areas, right? The one on the right minus the one on the left. Okay, so what's a much easier way to get this area? Yes, sir. Yeah, so they're triangles. So we can just use your freshman geometry. So we can just get the area of this, which is 1/2. Base is going to be 2 1/4. What's that? 9/4 times height. So we need this dimension at -2. What's the value of the function? Is that -9? So we want +9 because we want area. So we get 1/2 base times height. So the base is 9/4. This height is 9 plus 1/2. What's that? 5 3/4. Is that 23/4 times height of this triangle, which is the value of that equation at x equals 6, 23. So that's a little quicker. So 0.5 times 81/4 plus 0.5 times 23 squared over 4. Use preview answer. Make sure it's what we want. 0.5 times 81/4. 0.5 times 23 looks right. Check. Green. Questions on that one? Okay, so those were the two that had the lowest, you guys had the most difficulty with. Hopefully that clears things out. So you're really understanding what integrals calculate relative to area, and then now you have to, if you could be asked for different things, and you'd have to manipulate your situation and manipulate the integrals to get what's being asked for. In this case, area means anytime it's below, you need a separate integral, we're going to take the opposite. And then that'll flip it into a positive area. Questions on this one? Okay, so let's look at some more examples, some more issues that come up with these different problems. So I think we left off last time with, did we get this one? Did we finish this one? At least we talked about it. So we're going to, we set it up, it didn't solve it. Okay, so this is y is 1/2 x cubed. So it's y equals 6, and I think at the end we found that that x value was 2, is that right? This was the 0.24. And just to remind you, we did, so with these area bounded, so these problems now are going to require what I talked about last time, or not require, but really highly recommend for your own ability to do lots of problems that we think about, the fact that we're adding a bunch of rectangles, or what I call strips, right? And so for this one, the area of the strip was base times height, and we said that the base was delta x, and the height was, how do we characterize what that height was first? We said it was a change in y, right? Do you see that the height of that strip is a change in y from the curve up to the line? So we can write that as y2 minus y1 first. But since we have delta x, we want to change that into x, so y2, that's the line. So 6 minus x. And y1 was the curve at the bottom, so that's 1/2 x cubed. So that is our area of just that one, and then we're going to imagine we're going to add those up from left to right. Starting at the y-axis, we're going to kind of add up all this typical strips. So starting with this tallest one here, the first one is going to be this one, right there. The last one is going to have like 0 height right there. And we want to add up them all in between. Adding up all those areas from there to there will get us the total area, right? And that's exactly what integral is, right? So the first strip occurs at 0. The last strip we found occurs at x equals 2. So that's a recap of that problem. So these problems where you have a region bounded by curves, when you do these elements, you're going to get area because your typical strip is a positive value, and we're adding up a bunch of positive values. So that will always give you area in these ones where you're configuring a region with lots of curves. You don't have to worry about net area anymore as long as you set up the typical element right. You're going to add them all together. They're all going to be positive. We're going to add them all together, right? By doing base delta x times that change in y, those are both positive for all the strips. So net area, you don't have to worry about that anymore, okay? On these ones where you're configuring a region with curves. So we know this will be greater than 0 and equal the area. Okay, so what about the region now bounded by these two curves and the x-axis? Let me erase here. So first of all, so it's the same two curves. We can keep that drawing. Can you see what we're talking about now? So what region is, when you use the same two curves and bounded by the x-axis, what region do you get? Yeah, so we're using the x-axis now here, and so the x-axis and this curve and this line is now this region. Okay, so now we want to find the area of that. So we can come over here and we can say, all right, let's do our typical strip. So right here, draw our typical strip. Some of you are thinking something. Go ahead. Right. Okay, so in this previous example, we took that typical strip, and the typical strip was the same for every strip in the region. It always had the line at the top and the curve at the bottom. Every one of those strips. Do you see that? But this one, if you look, here we've got these typical strips going from the x-axis up to the curve. When we get to this point, what happens? What about these typical strips over here? They're different. They're bounded by the line at the top. So one integral isn't going to cut it because we have two different typical strips to take care of. So we can say AS1 and AS2. Again, it's going to be base times height. What's the base? Still delta x. The height is, so now, the height, x coordinate, y coordinate, change in x or change in y? The height of that first strip on the left. Is it an x coordinate, a y coordinate, a change in x, or a change in y? This is the question you got to train yourself to ask. That's just a y coordinate. Okay, so I can write delta x times y. Which y coordinate is it? For the curve, so it's going to be the 1/2 x cubed. This one. Now the second, so this is strip 1, this is strip 2. For the second typical strip, delta x times that height of that is a x coordinate, y coordinate, change in x, or change in y? Another y coordinate, but it's a different y coordinate, right? So it's we still write delta x times y, but it's a different y because it's the y defined by this line. So delta x times 6 minus x, right? Okay, and so now the area is going to be, we're going to add up all this typical strips number 1. Those are going to start at x equals 0 up to 2. And then when we get to this point, now we got to sum up a different type of typical strip. So we got to start with a new integral. Sum up from 2 to 6. These typical strips, which we got as 6 minus x dx. So that will do it. That's going to get it. Now, we can't use geometry. We might use geometry for that second one because that second one's just a triangle. So you could, theoretically, you could break this up. You could just use 1/2 base times height on that, but you have to use an integral on this one, right? This is an x, the top of this is x, 1/2 x cubed. So this left-hand kind of ramp is, you need the integral. Second integral is optional. You could do 1/2 base times height. Questions on this? And then some of you are thinking something else. Oh, yeah. Uh-huh. But this is what? This is the area of a typical strip. Base times height. So that's just one. What I drew. So this is the area. This is actually dA of strip 1. And then integral means sum them all up. I don't know if I answered your question. Try me again. Okay. Yeah. So, but the approach is that you find the area of one of these, that red thing right there, one of those. That's this. That's this actually. That's the area of that red strip, and then the integral will allow us to add them all up from 0 to 2. So the first one is this one with 0 height, and then we're going to add them all up, a zillion of them. The last one's the tallest one here. And that's what the integral does. It adds up all of these things, sums them all up. Is it better? No, because the y-coordinate, see the y-coordinate, what does the y-coordinate give you? The y-coordinate gives you the distance from the x-axis up to the top. That's a y-coordinate right there, right? The height of that strip is the same as the y-coordinate of that point because it's the distance from the x-axis up to that point. So it has nothing to, there's no distance down here. Do you see it now? Yeah, that height of that thing is the y coordinate of that point from the x-axis up. And there it is right there, y. Okay. Any more comments about this problem? Observations? Yes, sir? Yes, we can do this differently and only have one integral. But not this way. You can't do it. You can't make your strips that way. If you make your strips vertical like that, you got to do two integrals. But what's another option? Make your strips horizontal. If you make your strips horizontal, what happens? So let's take a look at a typical strip when we make horizontal. So now what? So we're still, I'll do this in blue. A blue typical strip there. So if you do it a horizontal strip, start again. Wow. There we go. Okay, so we'll call that S3. It's also a rectangle, so base times height. So we'll say the base will make the base always that's teeny, the slim dimension. Okay, so when we do base times height for these sticks, so these slices, strips. Whenever we do the strips, the base will be the tiny dimension. So what is the base in this case? Delta y, right? So the tiny dimension now is a little change in y, delta y. And so then what about our height? The height would be this thing laying down on its side now. X coordinate, y coordinate, change in x or change in y? Now it's a change in x, right? So it's a change in x. So it's going to be x2. Change is final minus initial, right? So it's going to be delta y times x2 minus x1. Okay, so this strip method that I'm teaching you is going to empower you to do all kinds of problems that if you just memorize something quick and easy of just setting up integrals fast, will not help you do problems in the future. So really learning to do this, practicing this, when we get to volumes and when we get to physics problems, this is going to be really, really helpful, okay? This is empowering you to do many, many more problems. So again, I encourage you to do this. My experience is more than half the class just blows me off. I got my own way of doing it, okay? Well, then you're going to have your own way of doing like 5 or 6 different types of problems when this could do it all. This could do all the kinds of problems we're going to see in the next couple of weeks, okay? So again, so our height, the base is going to be that little delta y, and then the height is a change in x, x2 minus x1. So now we just got to figure out what those are. What is x2? Because we have delta y, we got to get that in terms of y. So x2 relates to which function? The line, right? So x2 means right is going to be the line. It's the line's x coordinate in terms of y, which is 6 minus y. So x. So this is our x2 now for this blue strip. That's x2 right there. So x is 6 minus y. And then minus x1 will be that's the x coordinate for the curve. So you're going to have to solve for x. Do you see this? So x1 is this thing solved for x in terms of y. So it'd be 2y cube root. Do you see it? And now, what about this? What advantage do we have to this? Where's our first typical strip? At the bottom, the longest one, right? The longest one down here. That's the first one. And then we're going to stack them all up here, add them to the one that has 0 dimension up here. So what's true about orienting the strips this way? all the strips cover the region this time. So, because they all start at the left side at the curve and end at the right side at the line. So all the strips will be of this form right here, AS3. That's a 3. So the area is alternatively also equal to integral. So we're going to have our typical strip, 6 minus y minus cube root of 2y. Okay, and so now the first strip's not going to be on the left, it's going to be on the bottom, because it's in terms of y. The y value of the first strip on the bottom is 0 at the bottom, and then the last strip is at 4, y equals 4. 1 integral. So that's this one single integral is equal to the sum that we made before when we did it in terms of x. Okay, so sometimes you'll just have the choice, okay? And you can do it however you want. All right, so pick the easiest way. Sometimes it'll tell you, do it in terms of x or do it in terms of y, and then you may have to do a sum of integrals. Sometimes one way will result in an antiderivative that's possible to do, and the other way will result in an antiderivative that we don't have a technique for. So in terms of choosing which way, there's different factors involved there. What's being specified by the problem, what makes it easier, what makes it possible, okay? Sometimes, like, you would do it in terms of x, you get an antiderivative that's not doable by our methods. Switch it to the other variable, and you'd have something that's you can calculate. Okay, questions on this important example? But it's always good practice to set it up both ways. Set it up both ways. All right, so let's take a look at one more. Okay, so again, here's example. This is an example of curves that you should be able to sketch without a graphing calculator. Notice these are x in terms of y, so they're less familiar, right? They're less familiar. So I'm going to give you one way to do this, and in terms of making the sketch. So here's a suggestion for making the sketch. We might not know offhand what x equals 1 minus y squared is, but we should know what y equals 1 minus x squared is. And likewise, we should know what y equals 2x squared is. So we can use the graphs of those that we should be able to sketch to help us sketch these, right? What are you doing? We're just switching x and y. We're just switching x and y. Okay, so let's just, over here, quickly draw these. Y equals 1 minus x squared. Is that going to open up or down? That's going to open down because it's minus x squared, and the vertex is going to be at 0, 1, right? So it's like a downward opening parabola moved up 1. And then y equals 2x squared is actually the easiest parabola we know, times 2, right? So we know that parabola has a vertex at the origin. Times 2 means all the y coordinates are twice what they would be. And that will stretch it up. Okay, so now we want to use this. We want to use that to help us sketch this region. We're just flipping x and y. Now the real region, okay? We're just flipping x and y. This first one, what? It opened on the negative or positive x or y axis. This is opening up on the negative or positive x or y axis. It's opening on the negative y. See, it's opening up along the negative y axis, right? So if we switch x and y, which direction will this open up on? The negative x-axis. And rather than having a vertex of 0, 1, it'll have a vertex of 1, 0. See that? So you just can use what you know about y equals 1 minus x squared and switch x and y. So it's going to have vertex of 1, 0 instead of 0, 1. And then this one opens up on the negative y-axis, so this will open up on the negative x-axis. All right, and then this one has a vertex of 0, 0, so still have vertex of 0, 0. This one opens on the what? Negative or positive x or y axis. This opens up on the positive y. See that? It's opening upward, positive y. So this will open up on the positive x. Be more narrow and skinny like this. My pictures are better today than this Monday. So here's our x minus 1. So here's what I've seen countless times. Students will solve these for y and put it in the calculator. And then their sketches will be wrong. Why? Yeah, when they come square root, you lose half of the curve. All right, when you do square root and you don't do plus or minus, then you lose half the curve. And if you graph that as y equals square root, just plus, you're just going to get the top half of these curves. So you've got to have some way, you can't rely on your calculator to graph these. You've got to have some method. Here's, I think this is a good method or something that you know how to graph parabolas that are x in terms of y rather than y in terms of x. Okay, so we need to find this area. And so it doesn't specify how we do it, so we want to think, do we want to use vertical strips or do we want to use horizontal strips to make our life the easiest? Vertical strips or horizontal? What do you think? Good question, sure. Yeah, it's okay. You really should know how to do this in the conventional system, okay? So you really should know how to sketch these easy functions. Yes, there are tricks you can do to get the problems right. Absolutely. And when it comes to web work and you're getting final answers, we can't stop you, okay? But just being in Calc 2, you should know how to sketch that in the conventional system. You just really should. Okay, so are we going to do vertical or horizontal strips to make this the easiest? Horizontal. Look, the same thing as last time. Vertical strips. First of all, there's two issues, vertical strips. Notice these vertical strips, the top and the bottom of the strip is with the same equation. So you can do it, but it's just throwing a wrench in there, right? So the bottom is x equals 2y squared, and the top is x equals 2y squared. All right, so that's a little tricky. And then as you move over to this side, you've got a different typical strip, whereas horizontal strips, there's one horizontal strip that is typical for the whole region, and we can do one integral. So let's do it fast. Ready? Base times height. Base is the small dimension, which is delta y. The height of that thing, the horizontal dimension is the height. Is it an x-coordinate, y-coordinate, change in x, or change in y? Change in x. Change in x. x2 minus x1. And by choosing these horizontal strips, look how easy it's going to be. What is x2? It's the x-coordinate of that parabola opening to the left. What's that? No solving required. It's just, what? This. 1 minus y squared. And what's x1? It's the x-coordinate of this parabola opening to the right. Well, that's just 2y squared. And we're going to go from, now we're going to add up all those typical strips. No, because the first one is at this negative, whatever that y value is. It's going to be some y value less than 0. So what are we going to do? We're going to have to set the x-coordinates equal. Set the x-coordinates equal and solve for y, and we get 1 equals 3y squared. So that's the cube root of 1/3, plus or minus. So this y-coordinate down here is the negative cube root of 1/3. And this y-coordinate up here is positive cube root of 1/3. Area of the strip, 1 minus y squared minus 2y squared. I went fast. Did I make a mistake? Check my math. So the first strip, that first horizontal strip, is at the y-coordinate at that bottom intersection point, which I had to find by setting the x's equal. And then the last one is just opposite of that. Okay, there'll be another set for Friday.